So no office hours for Emily today, but okay, welcome to class, everybody. Happy Friday. Weekend is nearly upon us. Okay, first off, a couple announcements. First off, I'm gonna have like a garage sale of stuff that's left in this class. Or I'm just gonna start chucking jackets for right answers, because pretty soon, it's getting out of hand. Somebody else left yet another bottle. So check around, or come pick up stuff if you feel like a jacket or water bottle. Come grab my office. Okay, another quick announcement. Emily can't do office hours today. She has a family thing. So to make up for it, she'll do a 2-hour session on Monday from 5 to 7. You want to take a note? Okay, a couple brief videos while the seconds before class. First off, we did the can demo, right, where we dissolve away the metal and leave behind the polymer, and it was terrifying. So here it is. We used really strong acid on accident, and it's just bubbling really strong acid everywhere. The fume hood had acid all over the place. We had to do a massive cleanup, but it worked, right? It actually worked. We dissolved away the polymer, or the metal, and it left behind the polymer. But then the problem was that it's actually extremely thin polymer, and it is really easy to rip and tear. And so in our efforts to get all the acid off, which was everywhere, we actually tore it to bits. So we will bring it on Monday, but the lab, we couldn't get to it this morning. So we will bring it on Monday. You'll at least see where there is polymer attached to metal. It's just not the awesome demo we'd hoped for. I do want to show 2 other quick demos, starting in class. I think I mentioned that there's organic electronics. So here's just an example. This came out last year sometime. So it's one of the new LG products, where you can see that TV, he's flexing it. That entire, they're calling it wallpaper TV, is flexible because it doesn't have, right, mine's just boggling. This should be boggling your mind, right? Organic electronics, and it's just the beginning. We're just gonna see cooler and cooler things with the organic electronics. And then the other one I want to show you, which I think is even more amazing, not this guy, is this. Last year, I actually lost my mind in class because this happened right before class when I came. But it's unreal. These researchers at the Leibniz Institute in Germany came up with a self-healing rubber, and check this out.
Is made of long, strand-like molecules tangled and bound together. A process called vulcanization has long been the standard for curing rubber to make it durable, but still stretchy. When rubber is pierced or torn, critical chemical bonds break and can't be revulcanized, making a damaged tire useless. Now, Amit Das and his colleagues at the Leibniz Institute have modified a commercial-grade tire rubber to avoid the need for vulcanization. Their carbon and nitrogen additive lets rubber reform crucial bonds. When torn, their rubber can recover the durability and elasticity that vulcanization gives. In their experiments, the cut in the rubber healed itself at room temperature, meaning a punctured tire could fix itself while your car sat in the garage. A little heat made it heal even faster. After 8 days, the rubber can withstand pressures of more than 750 psi. That's about 20 times the normal amount of pressure on a tire. ACS Headline Science is produced by the American Chemical...
Sorry. Okay. So, where we left off last time. Last time we sort of gave you a rundown of the history of polymers. In the class today, we're going to talk a little bit about how you make polymers through the process of polymerization. I'm going to talk about just a few of the important engineering polymers that we use. I'll describe some of these later. Okay? And so let's start from here. So most polymers are based off of hydrocarbons. In fact, most polymers that we get, the cost of polymers are tied to the cost of oil, because oil is the most common precursor, petroleum, right? It's just the way that we get most of our polymers. So Huntsman Chemical, one of the huge polymer manufacturers right out here in Utah, when they charge something, it's tied to the cost of oil at that given time. Because they're organics, they have carbon, it's unsurprising that they're dominantly covalently bonded. And we know that carbon has its 4 electrons it wants to share with 4 other, so carbon would like to make 4 bonds, okay? So if we assume that it forms single bonds, then every electron that it has of its 4 is going to contribute to one of those single bonds. It can also form double and triple bonds. These are not like out of bounds. And we see examples of that. Say like ethylene. Ethylene is this molecule. Oops. So you've got 2 hydrogens on the end bonded to a carbon, but this carbon is double bonded to another carbon, which is bonded to 2 hydrogens. Right? So in all, if you count from the carbon, it's got 1, 2, 3, 4 bonds, right? It's just that it's double sharing with the carbon in the middle, right? You can also have acetylene, like the material they use in welding, right? Acetylene torches. Now it's a triple bond, right? But in average, like, it's pretty easy to count that carbon wants to have 4 bonds total, right? And so in the vast majority of polymers, since they have carbon in them, it's pretty easy to guess how many bonds they're going to have, okay? If there are only single bonds, then we say it is a saturated polymer. Have you ever heard of like saturated versus unsaturated fats? A saturated fat is something that has only single bonds. Saturated fat has some double bonds or triple bonds in there. Okay, the paraffin family is maybe the place to start with polymers. Paraffins are just carbon and hydrogen, right? And paraffin, if maybe you've heard that word before, paraffin is just a wax, right? A paraffin is a wax. And so when we think of methane, ethane, and propane, we don't think waxes. But that's because they're the shortest carbon chain members of the paraffin family, right? As you go towards longer and longer carbon chains, so more and more carbons present, they start to go less like gases, less like liquids, and more like kind of gooey solids like waxes, right? So in fact, the melting and the boiling point of paraffins, and all polymers really, increases with chain length. It's starting to plateau, right? It's plateauing out, but it increases with chain length. So the question is, and I want you to turn to your neighbor for this, why on earth should melting point and boiling point be correlated to chain length? So discuss with your neighbors. Okay, who's got an idea? Go ahead, Antonio.
So because there's a longer chain, there's more opportunity for London dispersion forces in causing electrons.
Exactly. London dispersion force is just another word for second. Perfect. Just what we needed in the middle of class. Okay, what is the London dispersion force? It's the same thing as a van der Waals forces. And van der Waals forces are what again? How does the van der Waals force come into existence? Has to do with either a permanent or a temporary dipole. Right? We'll say either of those for right now. Right? So if you have a polymer chain, like a long chain, it's a paraffin, it's just carbon and hydrogen. The backbone is carbon, it's got hydrogen sticking out the side. The longer that is, the more likely that you can induce a dipole, and then that chain of, like, if these are polymer chains, right, that now they can interact with one another and be bonded to one another. So the longer it is, therefore the more bonding, the higher the melting or the boiling point. Okay, we will start with 4. Okay. So that's exactly right. Basically, van der Waals forces increases with chain length, okay? Now, paraffins and all polymers, really, they don't have to be linear. There's what's called isomers that exist. Isomer is just iso, same, mer, means the same unit, right? So you can have something like butane and isobutane, okay? So butane is 4, so it would be carbon, 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 and all of these things that I'm not going to draw the H's for represent carbon-hydrogen bonds, right? Those little dashes, that represents a carbon-hydrogen bond. So you could have that's butane, right, for like a butane torch, but you could also have this, carbon, 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 carbon. I guess it's got one extra there, right? You could also have that, right? That's isobutane, right? So which one would have the higher boiling point, right? Butane or isobutane? I think that's actually a clicker question. Let's skip this one. Skipping. But this one. Would isobutane or butane have a higher boiling point? A or B? Which one would have the higher boiling point, A or B? Okay, answers in. Think of which one will have the stronger van der Waals bonding. Okay, answers in. Quickly. Are we good to end? Okay. Okay, people think butane or isobutane. What do they think? It is definitely butane. So let me call on the individual wearing the Argentine jersey, because I love Argentine soccer. Why is it butane?
Why is it butane? Because it's got a greater dipole.
Why would it have a greater dipole? I don't know if that's the quite right answer.
It has a longer chain, so the dipole is more obvious now.
Think of it like this, right? Here's our two chains, right? But this chain has like cancer growing off the side, right? So it's got that thing sticking off the side. So this thing can't get as close, right? Dipole interactions, the closer they are, the stronger they're going to be. So if you have isobutane where it's sort of forked and you got a side group, that prevents you from coming as close together, and so it actually weakens the bond, right? So side groups, whether they're whole other chains that go off the side or if it's just a different conformation like that, they reduce the boiling point because it's not as strong a bonding. Okay, let's talk about polymer. Let's see. So there's lots of different radicals that are possible for structures, right? So we have our main backbone, which is carbon, probably bonded to hydrogen, not necessarily though. But then at the ends of these things, oftentimes we have a different, what's called functional group sticking off the end. They could be methyl, it could be an ethyl group at the end, it could be a phenyl group, which is a sort of a C6 ring with hydrogen sticking off the end. We'll come back to that in a minute. Okay, polymer molecules. Oftentimes polymer molecules, things like you see here, these are way, way bigger than just the small hydrocarbons that we're thinking of, like ethylene and methane and propane and butane. These are like hundreds or thousands of those things put together in big long chains, right? Covalent interatomic bonds happen along this backbone, right? So if you're using a single bond, consider single bonding for a minute, then you're using two of your carbon's electrons along the chain. You're putting one electron forward to the carbon in front of you, one electron backwards to the one behind you, but you've got two extra electrons you can do something with. So you oftentimes bond above and bond below, right? Okay? So the polymer, the word polymer comes from the Greek. Mer means many, or means units, and poly means many, right? So many units or many parts, polymer. Polymer comes then from monomers, which is a single part, right? So you start out with a monomer, and if you polymerize it, you turn monomers into polymers. So here's some of the hydrocarbon groups we talked about before. If you want to turn ethylene into ethyl alcohol, you substitute one end group with an, instead of just ending in a CH2, you end it in an OH group, right? Methanol, alcohol, propanol, they all have this OH group on the end. They're all alcohols, right? And so forth with aldehydes, alkynes, amides, and so forth. I'm not going to expect you to know these. If you take OChem, you'll learn a whole lot more about them. There are also things like aromatic groups. Aromatic groups are things that have a C6 ring inside of them. So take phenyl, right? A phenyl group has this. So this is bonded to the chain, right? That's this. Our rest of our chain is maybe up here. But these are all just carbon bonded to hydrogens. Anytime you see lines coming together, you can just recognize that that's a carbon atom there. Short term for this is we just don't write the atom, the carbon there, but recognize there's one there. But if you look at this, it's only got 3 bonds, right? 1, 2, 3 bonds, right? So there's a problem. So we know there must be double bonds. So just like with graphene, when we talked about it earlier, there are actually double bonds. But this structure is resonant with this structure, where if we do the double bonds over there, right? So they're actually alternating, or rather the double bond is shared between multiple sites, okay? So how do we go from monomer to polymer? This is maybe the more interesting part of the lecture today. Let's say you start out with ethylene, right? This molecule is ethylene, right? How do you turn that into polyethylene? Polyethylene is, which one? One of these. Polyethylene, the most common plastic, right? Plastic, polymer, same thing. Well, same word, basically. It means the same thing in this class. This, you get this from that, but that's a gas molecule, that ethylene molecule. This is clearly a solid. It's a pretty hard solid, right? So how do you go from there to here? You have to polymerize it. Polymerizing means you have to go, well, look what's different. This is polyethylene, this big long chain that we keep on going. it has single bonds between the carbons, right? Whereas this ethylene has a double bond. So what we have to do is we have to introduce something that's going to break that double bond, right? And then it's going to do the following. So let's say we put in something like bromine, Br2, which will dissociate into 2Br. They draw a little dot. That means it's a radical, right? So this bromine free radical is now able to go in and attack that double bond and break it. So now you've got bromine bonded to carbon, which is bonded to 2 hydrogens. You've got this like that, right? We just did that by splitting it. But now count the bonds. You've got 1, 2, 3, 4 bonds for this carbon. It's happy. But this one's only got 1, 2, 3. So it technically has this leftover electron. And now it's a free radical, right? So this thing finds another ethylene molecule. What's happening? Am I not plugged in all the way? Am I bumping it? This is one of many different types. This is one of the most common ones, right? You add what's called an initiator. The initiator creates a free radical, such as bromine. That attacks a monomer and breaks a double bond commonly. That double bond, since it's not there, you now have a leftover free electron that can attack another one. And so this just keeps on going until you run out of new ethylene molecules for this to attack. Or, here's the other thing that can go wrong. If another bromine molecule, free radical, comes over here, it could cap this thing. So now you've got a long chain of polyethylene capped with bromine groups on the end, right? And that would terminate this. It's now no longer free to keep polymerizing. That'll come in, that'll be important later.
So when we did the thing making the homemade solar putty, we were using the, what's it called, Max or whatever.
That we used boron. That was cross-linking. Cross-linking is not quite the same as polymerization. I mean, there's some similar elements to them. We'll get to cross-linking later today, I hope. Okay. Yeah, Polly?
So if we take the free radical and it goes and attacks that carbon double bond,
yep.
how do we get the bromine off it while not have
You don't. I mean, you could substitute it when you're all done, and there are a lot of. So if you guys take organic chemistry, I know the material science has to take at least one semester. I don't think mechanicals do though.
Well, I mean, I take it okay, so I just don't.
Oh, so there's reactions. Basically, you pick something that wants to be there more than the bromine, so it displaces it. So there's a series of reactions that are possible. We're definitely not going to cover them in this class.
Or you could just add a very small amount of bromine and not have to worry about it, right?
That's another thing. Like, let's say you add a tiny amount of the initiator. If you add a very little amount, then there's very few chains being formed. And if you let these things polymerize all the way to completion, you have a small number of incredibly long chains. Yeah, that's another thing, and we'll come back to that actually. So we keep on drawing this polymer like a straight line, but it is in fact not a straight line, and it is not this. And that's a fine way to do it when we're talking about it, right? But in actuality, we know that electrons don't like to overlap with one another. They like to be separated. Carbon has 4, and I think the other day we mentioned that the best way to separate 4 things around a sphere is a tetrahedron, right? So if these are like my 4 things, right? We do 3 below and 1 above, right? Kind of see this? These 4 are as far away from each other as pretty much they can get, right? This tetrahedral shape. So what's the angle between this thing and this, right? It's 109.5 degrees, right? So that number is going to be important in this chapter. Right? So in actuality, we draw it as a zigzag like this. Is a more common way to draw the structure. And you recognize that this is 109.5 degrees, right? Another way to do it is to draw the carbon with those 2 in plane, this one coming out and this one going into the board, right? If those were hydrogens. The upper one, the left one, would be in plane, but then that means this hydrogen must be coming out and down. The other one must be going out and back. Or sorry, back and down, excuse me. Okay, let's talk about the first, let's run down of some of these polymers, the most important ones anyways. These are the ones I expect you to know sort of for an exam. Polyethylene. Polyethylene is the most common plastic. It is used for almost everything, right? Packaging, bottles, toys, all sorts of things. It's the most commonly used plastic. It has this repeat unit. It has carbon, bonded to carbon, bonded to a hydrogen, bonded to hydrogen, bonded to hydrogen, right? It is the simplest polymer that we can talk about. We've already showed its structure a few times, right? Polyethylene, right? So this right here is what's called the repeat or mer unit, right? Technically, you could even take one of those, but the convention is to take 2 carbons, right? That's the repeat unit. So if your chain is some huge number of them long, it's going to be in integers of of these things, right? We'll come back to that later. Now there's lots of different flavors, right? I don't know if flavor is the right word, of polyethylene. There's LDPE, HDPE. In fact, if you've got a bottle that's plastic or a calculator or something that's made out of PE, if you look at it, it'll oftentimes say HDPE, LDPE. Maybe you've seen this before. Or if you've seen the recycle number, right? The recycle number will have a number between 1 and 9. That corresponds to which type of plastic it is. Because when you look at this, like I'm pretty sure that this is Teflon, but without testing it, I'm not even sure. And a layperson has no idea what this is. I actually have no idea what this is. It's probably polyethylene because it's really light, but I don't know, right? So they put numbers on things to help us know how to recycle them better, right? Because there's lots of different plastics and you don't want to mix them usually. Okay. Next one is polytetrafluoroethylene, PTFE. This is Teflon. It's also known as a fluorocarbon. So this one's definitely PTFE. I'm almost positive this is because it's slippery, right? And it's white, right? Fluoropolymers or fluorocarbons are incredibly important because they don't stick, right? They're hydrophobic, water like beads up on them. They have extremely low coefficient of friction, the third lowest of any solid. They're unreactive because it's carbon bonded to fluorine. That fluorine and carbon makes a very strong bond and it can't be bothered with anything else, right? You put it in the presence of acid that has, these oxidizing radicals, doesn't care. It's happy, right? So it's a very good polymer for chemical inertness. They use it for lubricants. They use it for all sorts of things. And one thing I think is interesting, it is the only substance on the planet that a gecko cannot stick to, so we have to watch the video, obviously. Not happening. Not today, gecko. Right? So that's amazing, right? However, it's the benefit of being chemically inert can also lead to some downsides, right? This stuff, so you've got a chain, right? You've got some long chain. Imagine these are all just carbons bonded to fluorines. It is inert. You cannot attack this with like regular acids and things. Well, the problem is, if this is a chain and this is another chain of Teflon, well, we can't make these things stick to each other, right? They have some van der Waals bonding, but oftentimes we like to augment van der Waals bonding by bonding them together, just like Legos, right? We stick them together. That's called cross-linking. That's what Alex mentioned earlier. When we added the borax to the glue, we were cross-linking it. We were making these strands stick to each other. But these are so inert that it's hard to cross-link them with anything. And so because of that, you don't really form very, very strong bonds between these things. And so they're actually prone to sliding past one another, especially under sustained load. Sustained load and the plastic deformation that results from it is exactly what we've already talked about. That's creep, right? Teflon is actually very susceptible to creep because these chains, they don't bond with one another. Kylie.
So how do they make the melting point so high?
Why is the melting point so high? Good question. Why is the melting point so high? So they have van der Waals bonding, right? These things, they're very, like fluorine is a very electronegative atom, right? So it wants to pull those bonds very strongly. So there is a dipole present on this thing, which can be, an induced dipole. So these things can form strong van der Waals bonds, but a van der Waals bond is drastically weaker than a covalent bond. So when this actually breaks down, the reason why you can't use Teflon in like a fire, like too hot, right, on a pan or something, is because you will eventually break the covalent bonds along the chain, right, or between the carbon and the fluorine. I don't know which one breaks first, right? If that happens, then you're out of luck, right? Okay, that's Teflon. They use it for gaskets. You guys have probably used it. Teflon tape, right? If you've got a seam or a gasket, we like to put Teflon in there. But it's actually not great if it's going to be under a sustained load for a very long time because it will creep. And creep will eventually blow out your gasket, right? So it might, and in many instances, it is better to use rubbers, right? Oh, we'll get to rubbers later. Okay, PVC, polyvinyl chloride. So if you start out with polyethylene, right, which was carbon bonded with hydrogen all around it, you take out one of the hydrogens and put in a chlorine ion, you've got PVC, polyvinyl chloride, which is used for all sorts of things. This is one I think we mentioned the other day that it's pretty remarkable. It wasn't invented until the 70s, which blows my mind because this is everywhere. PVC pipes, you all have this in your garage. You have it in your homes. It's everywhere. PVC is innocuous, right? There's different, just like there's different flavors of polyethylene, LDPE, HDPE, we'll talk about those mean later. There's different flavors, if you will, of polyvinyl chloride. You can add additives that make it rigid or make it not rigid, right? So you can have leather pants, right? PVC pants, should the whim strike you. Or you can have very rigid pipes, right? Both are possible, it just depends on the additives you add to it. This has pretty crummy thermal resistance, right? PTFE is good too. I should know the number, 300 or 400, I think. It's good to relatively high temperatures. Polyvinyl chloride, 120 degrees C. So boiling water is 100, right? So we're getting pretty close to where it's going to be decomposing in just boiling water. So that's going to be important for applications, right? Because before it decomposes, it's probably going to soften and it's going to change its mechanical properties, okay? Next one, and so polyvinyl chloride is the third most used polymer. So polyethylene is number 1. Number 3 is polyvinyl chloride. Number 2 is polypropylene. Polypropylene, you start out with polyethylene and you replace one of the hydrogens with a methane, right? With a methyl group, right? The CH3, right? So these are, again, they're not drawn, but it's just understood that these would be hydrogens. So you've got hydrogens bonded on 3 of the sites, and one of the groups is a methyl site, CH3, right? So a CH3 is bigger than just a hydrogen, right? A chlorine is bigger than just a hydrogen. That'll be important in a few minutes. This is pretty rugged. It's chemically inert. They use it in packaging and textiles. They actually make ropes and carpet regularly out of our clothing, right? They make all sorts of things out of polypropylene. The chain itself can be degraded by UV light. UV light or heat can cause these bonds to break. And once it breaks, right, imagine if this thing breaks, you've got a chain, right? If something causes that to break, now you've got free radical. That's a bad thing. Then it can go on and attack the polymer elsewhere. So that's not a great thing. So they put things in polypropylene and many other polymers to intentionally absorb UV light so that the UV light doesn't get absorbed by breaking polymer chain, right? So they add things like carbon black, like rubber tires. Why are rubber tires black? Because they're full of asphaltenes, black things that basically absorb light. It's a cheap filler and it also blocks UV light. It absorbs UV light so that light doesn't mess with the cross-linking that you've put into it. Okay, there's polystyrene. Polystyrene, again, start with polyethylene, but instead of swapping it for what we talked about before, now we're going to put in a phenyl group, right? Phenyl's the right word there, right? It is a phenyl group, right? Yeah? Jimmy? I get the Jimmy approval? I think that's the right word, I'm pretty sure. Right? So this is a much larger side group sticking off the side, right? Polystyrene, if you make it dense, it is hard, clear, and brittle. Now, polystyrene, this is also styrofoam, right? So you don't think of styrofoam as being hard, clear, or brittle, and it's not. How they make styrofoam, this is actually pretty interesting. They'll take styrofoam and they start out with polystyrene little beads that have some pentane in it. It's got some organic molecule that can dissolve, pentane, right? They heat it up to 200 C in the presence of steam, and in that steam, sort of very high temperature steam-filled environment, the pentane can escape, and then steam and air can go into it, and it expands by 40 times its volume. So these little tiny beads grow into, if you've ever taken styrofoam, like in an Amazon box you got or something like these things, it's made of a bunch of small little beads, right? You can see them, they're like this, like a corn kernel. They're stuck together. They then take those little individual corn kernels and they make giant bricks out of them by just pressing it, basically, right? So that's polystyrene. It's actually flammable. Now, how about this? Even though it's flammable, you can take and you can boil an egg in a styrofoam cup by placing the egg in a cup that's filled with water. I haven't used this link in a while. Maybe it's still up. Yeah, right? So you can boil water in this, but we just said polystyrene is flammable. So what's happening here? How does this work? Yeah, basically it's polystyrene, so it's expanded styrofoam. So it's porous. It's a bunch of these little beads stuck together. So water can actually diffuse that through that pretty easily. And when it diffuses through, it gets to the surface where now you've got the fire, and it's evaporating. And as it evaporates, it's cooling the surface below it, right? It's constantly cooling it. So once you evaporate all the water, yeah, you betcha it's going to burn, right? But it's very permeable to moisture is the key feature there, right? It is not biodegradable. We use a ton of this, and it's not biodegradable, which is why I think companies like Amazon use it less and less than these other recyclable I think they're actually PTFE packets of air, right? Other things to provide packaging. There's PMMA. This one's harder. I won't expect you to know this structure. Polymethyl methacrylate is also called acrylic. If you've ever heard people talk about acrylic glass, it's not a glass, it's a polymer. And it's a polymer that they use to replace glass because it's lightweight, it's low temperature, like you can melt it and cast it at very low temperatures relative to glass. It's more shatter resistant than glass. And it's, polycarbonate's an even better shatter-resistant polymer for glass, but it has some other benefits relative to polycarbonate. Next up is Bakelite. I've mentioned this a couple times in the semester, but Bakelite is the plastic in your grandma's house. If you see like old phones, old cheap jewelry, right? This is Bakelite. You might even think it's a ceramic looking at because it's really hard, right? This is our first polymer that we're talking about that is not a thermoplastic, but is a thermoset. We'll talk about what that means in a moment. This is also a 3D one. Most of the polymers we've done now have been long chains. This one's not chains, it's a 3D network. This is how it works. The structure looks like this. So there's a sort of benzene ring to start with. When they draw the circle in it, that just means that it has the double bonds. That's shorthand for where the double bonds are. And then you've got hydrogen sticking out here. But here you've got a CH2 bonded to something, CH2 with another bond to something, and this one, a CH2 bonded to something. So these can all connect to other of those repeat mers, I guess you'd call them, right? And because there's 3 directions, you don't, not just 2, you can have more than just a line, you can have a 3-dimensional network structure, right? Because it's a 3-dimensional network structure, this is a pretty hard, strong polymer because it's covalently bonded in all dimensions. Plastics, they're van der Waals bonded between the chains, and so they're not very strong, and they melt at pretty low temperatures. This thing will not melt because you can't just overcome van der Waals forces. You have to break covalent bonds. And once you give it enough heat to break a covalent bond, it typically is catching on fire because that releases a lot of energy and it keeps on burning, right? So this will not remelt. Most of the plastics we've talked about now, polystyrene, right? If you get it hot enough, it'll melt. Polyethylene, polypropylene, polyvinyl chloride, these things melt. This one will not melt, it will burn, right? So it's toast, right? That's the difference between a thermoplastic and a thermoset. I'll come back to that in a second. Okay, nylon 6,6 is this polymer. Nylon 6,6, long name, polyhexamethylene adipamide, right? They call it nylon 6,6 because you've got carbon, 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 1, 2, 3, 4, 5, 6 carbons, and then over here you've got carbon, 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 6 more, right? So it's just shorthand. Nylon, the name where nylon comes from is actually not totally known. There's a, I think, racist reason for what it probably means, and I'm not going to say it, but that's, according to Wikipedia, I think it had racist origins, the name nylon. Regardless, it's a very commonly used material. Nylon is these things. These are both nylon. It's a very tough, strong plastic. It's pretty hard and brittle sounding, right? They use it for zip ties, ropes. You can actually see how they make this. This is the first example where you can have a co-polymerization, where there's not just one mer, but there's multiple mer units that come together to form it. So one of these years I'm going to do this in class. I've not done it yet. But basically, nylon 6, oh, this is nylon 610, very similar. To make it, you pour in 2 monomers, and they actually face separate. One's denser than the other. So you see 2 layers of liquid there. One is one monomer, you got the other one. Right? So here's the structure. It's made of this monomer. This one's like green and yellow, right? So what happens, where you pour these 2 together, you get polymerization at that interface, right? And if you grab that and start drawing it out, now they can keep on mixing. That interface just keeps on growing, so you can actually just put it in like a glass rod and they twist it. And this is called drawing the whole nylon. This is just a very easy way to make it. One of these years we'll do it. It's kind of gross looking, and it just gets grosser, right? So that's nylon 6,6. Obviously, once you take it out, you saw that that was not like a nice continuous fiber. So what they do is once you created the nylon, then they melt it and they draw it. Polymerize it, that's one easy way to There's PET, you probably have heard of PET. PET's been in the news in the last 5-10 years, and it's been much maligned. PET is a very hard brittle plastic they use it for bottles. I'm pretty sure that this is PET. It's not labeled. I haven't checked it, but I would wager that this is PET. I think it's very hard. Nalgene bottles made out of this. It's so hard and brittle, and it's not very easily processable that they add what's called a plasticizer. They add something to this to make it a little less rigid, so it's easier to form into shapes and stuff. And that's why it's in the news. That plasticizer, they think when you make Tupperware PET, that it's leaking out, right? As you put your microwave burrito in there and you nuke it, that plasticizer, they're afraid that it's leaching out into your burrito and getting ingested in your stomach. So, anyways, why is it so hard? Well, this is different. Look at it. You've got an oxygen in here as opposed to a carbon, right? You've got oxygen right there. And then you've got this whole aromatic ring as part of the backbone, right? So that's going to greatly increase the strength of the Kevlar, which is another extremely strong polymer. It has several of these aromatic rings along the background. Just makes it very, very strong. There's polycarbonate. Polycarbonate, again, it's a very strong polymer, very shatter resistant. It's got 2 of these aromatic rings along there, right? This is what they made, well, if CDs existed anymore. It's what they made CDs out of, right? It's very tough. They make bulletproof glass out of this because it's very transparent, better than glass actually, but it's very, very shatter resistant because it's not a brittle material, right? But it has very low scratch resistance. So if you made CDs, this was like the bane of me in 8th grade, was all my CDs were scratched. They actually started with polycarbonate and then they had to like coat it with a much harder polymer, right? And I am forgetting what they used for that. It's something. Okay, those are the important polymers. There's many other ones that are important. We didn't even talk about Delrin. Delrin's you'll probably use it if you are mechanical engineers. It's a commonly used one because you can machine it really easily. So there's other ones. We definitely did not cover all the polymers. There are way, way more. This is, I think, a flavor and a good enough for one for this class for now. Let's shift gears and talk about molecular weight. So molecular weight is just a measure of how long these chains are, right? Most polymers are chains. So how long is the chain? The molecular weight gives you a measure of that. So we have amount of polymer written here. I'm going to get rid of that and write number of strands. Right? Number of strands is, I think, a better way. Number of strands, you can have different molecular weights if you plot number of strands versus the molecular weight, right? If you have, so this is experimental data. You could actually measure a line like this. And we won't get into tools that can measure that, but they're out there, right? And it says that's the number of strands as a function of molecular weight. So there's number average molecular weight, MN, number average, and there's MW, which is weight average. So the number average is basically if you took the total number of strands and you know the number of strands somewhere in the middle, right? If there's 1,000 strands, you figure out what's the average molecular weight just out of those 1,000 strands, right? So that's going to be this one, MN. And then there's weight average. Weight average is going to be shifted off to the right of this peak, right? Why is it shifted to the right? Because the strands over here, even though there's way fewer of them, they weigh a lot more. Fewer, but weigh more. Their molecular weight is much, much higher, right? Because they're like maybe 10,000. These things get to crazy numbers, right? So the weight average will be shifted. These won't be the same number exactly, okay? So how do they calculate this? They generally, you'll see something like this. You'll see a table that says fraction. And this will be either fraction by weight or fraction by number. And then it'll give you a range, like molecular weight range, right? So they might say like 10 weight percent goes between 0 and 1,000 grams per mole, right? And then they'll say, and then you've got another 30% by weight that goes between, 1,000 and 10,000, right? And maybe the last like 60% is above that, greater than 10,000, maybe up to like 100,000. So how do you determine the number average molecular weight and the weight average molecular weight? Well, you'd have to have a table like this. From this table, we're given the weight fraction, right? So weight fraction is going to be WI, right? That's WI, our weight fraction. And then you need MI. MI is the mass of the polymer in that range, right? So in this case, we're going to take the average. You'd say 500. Here you'd say whatever the average is there, and the average here, right? And you'd basically just add them up. You'd say, all right, 0.1. So in this case, we'd say 0.1 times the average. So in this case, 500. Plus it'd be 0.3 times the average there. What is that? 5,500? I think. Anyways, and so forth, right? You keep on doing that. Now, if you wanted to calculate the number average, I would have had to give you another column in this table which says the number of strands, right? The number fraction, okay? But it's pretty straightforward. You just add these things up based off of some average value. If you want it to be more accurate, then you find a way to measure molecular weight within smaller and smaller windows. As it approaches smaller and smaller numbers, this gets more accurate. Because this is a very bulky histogram right now. The more narrow you make it, the more accurate it will be. Alex?
Couldn't you figure out the number of strands if you gave us a density per unit?
Density comes in later. We'll get to density in a minute. It has to do with crystallinity. We'll come back to that. So there's a couple examples in the book that I'm going to have you do for the homework next week, I guess after the exam. I suppose I'll assign it this Wednesday, but it won't be due until, I guess not the Wednesday after the exam, but probably 2 Wednesdays after. I'll double check. Anyways, you'll have a chance to do this. 3 Wednesdays after. Right. You're right. Fall break's coming. Anyways, you'll get a chance to see this. I'll make sure you have at least a week to work on it. Don't worry about it. Next off, and maybe more importantly, is the concept of degree of polymerization, N sub N or N sub W, where again, degree of polymerization can be either calculated based off of the number average or the weight average. So if it's based off the number average, then you take the molecular weight based off of the number average and divide it by M bar, right? So M bar, first off, this is M with a hat, right? That's this one that we've calculated up here, right? Same thing, right? And then small m bar, that's the mass of each individual repeat unit. So in polyethylene, remember that's 2 carbons bonded to 4 hydrogens. So you just figure out the mass of 2 carbons plus 4 hydrogens, right? And it's 28, right? It'd be 28. And so if you take the total weight average divided by that, then you get the degree of polymerization based on weight, or you get the degree of polymerization based off of number if you divide it by the number average, okay? Now, what if you have more than 1 mer in the structure, like nylon 6,6, right? Nylon 6,6, you could do it 2 ways. First off, if you know that you always have one of these right next to one of those, then just treat the whole thing as 1 mer. If you don't have equal amounts, maybe you have 2/3 of this one and 1/3 of that one, then you need to multiply by the fraction of those, right? So we'll do an example of that in a clicker in a moment. Okay, so we have 10 minutes left. I didn't think we'd get this far. Are there questions? Am I going too fast? What questions are there? It's coming. Patience, it's coming. Are there questions on polymers so far that I've gone too quickly through? Yeah, Chris?
Sorry, I guess it might be a little off topic, but does PTFE actually melt or does it sublimate?
PTFE is interesting. It does not melt really. When they make this, how do they make it? It doesn't melt, and you can't cast it into this whatever spindle sort of shape thing. Instead, they do powder processing. They have found ways to kind of make it melt now, but they do what's called powder processing. So I'm a big ceramics fan. In ceramics, these things don't melt until like bonkers temperatures. So how do you make ceramic components? You have to start with ground up little particles of ceramics, and you pack them together into some sort of shape, and then you do what's called sintering. And sintering is the process whereby these individual particles sort of diffuse into one another, and you'd like them to diffuse completely and get all the void space out. You don't usually ever get all of it out. There's always a little bit left over. Same thing with this. They actually take little particles of it and they sinter it together under like pressure. They sort of press on it and apply heat. That's how they make a lot of PTFE. I think nowadays they actually have additives to it that can locally make it kind of a little more soluble and easy to process. But I don't know for sure about that. We teach a great class on polymers in our department. Dimitri teaches an awesome class on it. So if you're interested, it's one of the favorites, I think. Yeah? Is that a fair statement? I think it's a department favorite. Maybe not? I think it is. I think it's good. So maybe we'll keep going then. Any other questions? Yeah, Paul?
Go over again. I'm just really confused on what you mean the difference between number average and weight average.
Okay, so if this is number of strands, right, then you have some average number of strands, right? In this case, we're assuming like the area, like maybe amount of polymers is a better way to put this, right? That is a fair way to put it. That you've got some average number of strands at some weight, right? Okay, so if you have 1,000 strands and you count up that there are 13 strands that are X long and you have 100 that are this long, that you could just take up out of those 1,000 strands, what's the average number length, okay? And then there's molecular weight, which takes into account that the longer strands, even though there might be very few of them, they could be incredibly heavy. And so it skews your molecular weight to the right. Okay? Yeah, Amy or Ali?
For that reason, is the number average
I think it would be more valuable, the number average, but it's harder to measure. It's way easier to determine the weight fraction. Like, we haven't even talked about the tools that we do to measure this, but determining them by number of, like, how would you do that? You have to be able to like look in it and count them somehow, but these things are so small that's not realistic. So how they actually measure it, I'm drawing a blank how they do it, but I know how they do it with weight average, and it's much easier to do. So I think, is there a way to convert between the two? I don't think so, but I better not give you a concrete answer on that. I better look that up. I think maybe not, but I better not confirm. Tyler?
Help us interpret this graph a little bit. Like, I think I'm still not sure what I'm looking at.
So you're looking at the amount of polymer versus the molecular weight of that individual type of polymer, right? So basically, say you did the polymerization, right? You added the bromine, and each one of those little bromines started attacking ethylenes, and some of those were able to go and get crazy long, but not very many. So you have some of them, some amount over here, that got crazy long. And yet some of them that didn't get very long at all, got terminated. And most of them are somewhere in between, right? So that's what this plot is showing. It's just saying amount of polymer at some individual molecular weight. So it's saying that if you looked inside a microscope and you could somehow see these chains, you'd have, you know, some of these little short ones, you'd have a lot in the intermediate range, and maybe one or two that's crazy long. This plot is just a way of showing that, right? It's just a distribution based off of molecular weight.
Okay, so it's just a plot of like your whole sample, basically.
Of your whole sample. If you could take like an average of what's there, since we know that there's not technically one average, right? There's not like there's one chain length everywhere. It'd be nice if there was. If it was just like everything was one chain length, that'd be great. But in reality, we end up with a distribution. And so we need to talk about that distribution. And there's two ways that we can do it. We can assign an average based off of weight or number. Technically, it'd be nice to have like standard deviations too, but I don't know if I ever see that reported. Alex and Danny.
What I don't quite understand is like, if you know like how much one strand is going to weigh,
Okay.
right? Because you have the density of the material, and so you know blah blah blah. Then wouldn't you be able to figure out how many strands there were of that mass or of that weight?
We'll come back to density. The problem with density is that these things aren't totally crystalline. If they crystallized perfectly, you could use density, but they don't. They have regions that are crystalline and regions that are definitely not crystalline, or some of them are not crystalline at all. So we'll come back to that next class. So Danny, another question?
Yeah, so when you say number average molecular weight, does that mean the weight of the average number of strands?
Yeah, so like you've got like 1,000 strands, and on average, you figured out what's the average length, what's the molecular weight of that?
So the number average is still a measure of molecular weight, it's just based on number of strands that make up that weight instead of...
Correct, rather than total weight of the fraction of your component, right? Let's end here and pick up here next time. Enjoy your weekend. What's that? One second, let me stop this.